I want to thank you for joining us for the final results presentation on alternative stream channel maintenance at bridge crossings. We'll ask that you hold your questions to the end of the presentation. It is being presented and it was funded through the Ohio Department of Transportation, Federal Highways, and being presented by John Witter and Dan Mecklenburg, both with the Ohio State University.
Great. Thank you, Jill. I appreciate it. Our project was the alternative stream channel maintenance at bridge crossings. I believe we started this back in 2013. Does that sound about right? And we've had some additional objectives added over time. Here's our research, our immediate research team. I'm John Witter. I essentially push a lot of paperwork so I can keep Dan free to answer all the hard science questions. You're going to hear from Dan here after I start this thing off. Part of our project team also was Peggy Johnson. She's at Penn State University and probably one of the world's leading experts at applying these practices at bridge crossings. So it was great to have her input. She helped us develop some decision aids as well as some post-construction monitoring protocols for this project. And then we worked closely with the folks at EMH&T here in Columbus, Miles Hebert, Christy Perkle, Holly Yaryan Hall, who helped do some of the engineering design, get these things on paper as well as the permitting, and we're very grateful for all the work that they put forth to help keep things moving. Before we get into the nuts and bolts of the science, I just wanted to take a minute to point out that this was a very collaborative project. It took a number of different entities, groups of people to help us have the successes we were able to have. We kind of diagrammed that with this concentric circles, and I'll tell you why we diagrammed it this way. First, on sort of the outside, we have the research section who helped put together the RFP, take the ideas, get it out there, help select a group, and which was us, and then they do the research administration. One of the most effective and efficient research administration groups I've had in the 30-plus grants that I've been awarded over time. And I just really want to point out all the effort that Jill Martindale has put forth in this project. She's actually the one that helps us figure out who within ODOT it is we need to talk to get to the next step. So a large part of our success is due to her guidance, and I just wanted to recognize that real quick. Also, our technical liaisons, we've had a number over time, Matt Perlick, Rick Rowe, Adrian Early has helped out, Matt Raymond, to help guide us on our research objectives, the additional objectives that we did, so we're really grateful for them. And then there's the research team. I kind of went through us on the beginning slide. But at the center of this circle, I decided that's where we wanted to put the counties and the district forces, because really their participation was critical to this project, because if we don't have them involved, we don't come up with solutions that are implementable. And early on in this project, there was a lot of resistance. We come to the table with these ideas, and they say, well, we have some tools. We say, well, we think these tools are better. We give them a smorgasbord of tools we could look at. With their feedback and their input, we start to whittle it down to a handful that we think are doable. And the really interesting thing about this is they started to throw in their ideas. They helped us innovate some of the processes, some of the materials that we looked at, and they came up with ideas, and they really contributed to this research in a big way to make sure it was something that was implementable in the end. So we're greatly indebted to the folks in the counties and the districts that participated in this, sometimes even though they were fairly skeptical, but I think we got to a workable endpoint, and now we're going to share some of those projects with you. Our objectives, first of all, we needed to assess what were ODOT's current capabilities and the practices that they use to do maintenance at stream crossings. So what do they currently do? But also what kind of materials can they gather for these projects? If we're going to ask somebody to do something different, it might require different materials. What sort of equipment do you have to do the work? What's the skill of the workforce to do this sort of thing? So that was our first step, to assess what current capacities were. And then we started to do the literature reviews. We looked at our experience in the stream restoration field. What sort of practices could we bring to bear to come up with more sustainable maintenance solutions at bridge crossings, where streams were impacting foundations, the abutments, the embankments. After we went through and we started to get a fairly narrow list of projects that seemed doable, how do we develop a decision aid or a tool to help guide engineers or county workers towards what's the right practice to address a particular problem? We worked with EMH&T to put the designs on paper, get feedback from the counties, but then to also go through some of the permitting processes that were required because this was federal funding. This is a point where Dan came in and he actually worked very extensively on site with each of the counties to implement these projects. And then he's gone ahead and he's documented that whole installation process as well as how are the sites progressing since they were installed. So we've got some educational materials, some videos we'll share with you today. So that after we walk away from here, it's just not 8 projects or 8 groups of people that have participated in that and then never do it again. We want to document that. So if there are others interested in undertaking these types of projects in the future, at least they can see the whole process that, that was involved. What does it look like, having some of those visual materials? Also, can we develop some standard drawings and technical specifications that they might pull from future projects? And then as well, watching these, so doing some post-construction assessment, how we look at if they're successful or if we need some sort of, to address some sort of issue that's occurred, how do we do that? How do we document that? ODOT has a lot of experience doing highway maintenance at stream channels, and in fact there's a whole manual on it. And if you look through the manual, a lot of the issues, the stream defects as they're categorized, what are the various areas? So streams will migrate. They're dynamic systems. They erode outer banks and deposit on inner banks. They move, and that can be a problem for a bridge that wants to remain stationary. We have developing watersheds or larger storms. We can also have streams that are down-cutting. They're transporting more sediment than is being supplied, and that can cause a problem for a bridge. Oop, there we go. So here we go. Here's the migration issue. You can see the outer banks eroding into the embankment, causing a problem for the stability of that bridge. Here we have an example of lowering. The more sediment being transported than can be supplied and could cause an issue for stability. As well as debris buildup on piers. You see a lot of this. I know the county maintenance forces are challenged by some of this, clearing of log jams so they have adequate capacity and can limit flooding and stresses on the structure. And there's a lot of guidance out there on how to deal with this. In fact, they're all throughout the peer-reviewed literature. Government documents, HEC 23, Bridge Scour, literally thousands upon thousands of pages of things that could be done to address this, and it's almost overwhelming to the point where someone trying to address these issues can get lost in all of this. So what do you do? What's applicable in this region? What are the sort of things that we can pull off? So we help sort through that. A lot of the techniques that you're going to see were developed in the stream restoration industry over the past 20 years. A lot of this started out with wealthy landowners wanting to improve the stream habitat for trout. So a lot of the early designs, biologists, ecologists were involved in this sort of thing. But what can we pull from all of that? This is literally $1 billion stream restoration industry. A lot of techniques are developed. I know developers now, when they develop a piece of property, may be required to do stream restoration. Oftentimes hundreds or thousands of dollars per linear foot. But what sort of lessons can we pull out of all that work and say what applies to streams at bridge crossings to smoothly transition flow, to transport not only the water and the sediment, and do that in such a way that's going to protect that structure, protect the public, the traveling public. one of the things that we can do, or one of the practices we can adapt, is actually guiding the flow. So if you think about that migration issue, are there things that we can do to shift and direct flow to keep that smoothly transitioned under that roadway? And veins, things like cross veins, J hooks, W weirs, you'll see examples of those in our project coming up. They're able to gently, smoothly transition that flow to where we want it to go. Here's an example of a cross vein. You can see it's higher on the outer side, lower in the center, and in the bottom there's a flood event. You can see it's directing all of that flow underneath the bridge. The other sort of category of projects that we think have a lot of applicability here around bridges is this idea of two-stage channels. An area I work in and up in northwest Ohio where there's a lot of agricultural drainage, and a lot of channels are designed to be trapezoidal channels, over wide. And what we've noticed over time is nature will come in and essentially build a small channel within the larger channel. And that's nature's way of trying to heal itself, to create this compound channel form. The inset channel will usually have faster flowing deep water because vegetation isn't in there. It's narrow and it's deeper, and that keeps the sediment moving through. The other thing, you can see the bulldozers on the small floodplain there. That can anchor the side slope, so it keeps the side slopes from eroding. So this is a very stable design. We see thousands upon thousands of examples in nature where an overwide channel was designed, a small inset channel within forms, and the reason that that works and is sustainable is because of that inset channel, keeping the water, keeping the sediment moving through, while the floodplains anchor those side slopes. So a very sustainable form. And how can we use that example at bridge crossings to come up with more stable cross sections? There have been 9 different projects that have been implemented as part of this research, and I'm going to turn it over to Dan here to talk about it real quick. But you can see they've been across districts 2 and 3, so essentially most of the northern half of Ohio, but 2 different types of areas, a more hilly, rolling terrain in the eastern part, and then a flatter terrain up in the northwestern part. And I'm going to turn it over to Dan and let you tell him about each of those projects.
Forgot your coffee, John. Yeah, I'm coming in on the middle of the presentation and came in on the middle of the project too after all the nasty meetings and environmental permitting and plans and specifications were taken care of, and I got to come in and play on the projects. So that's what I'll talk about is these 9 examples where we're kind of applying these concepts that John and I and the team have from kind of a stream morphology, stream form and function background applied to bridges. So let's look at 9 projects. This is the first one, and in our kind of where John and I have had a lot of experience in that flat agricultural drained landscape. We certainly know this terrain up in Sandusky County where a bars form and causing capacity issues with the bridge at this site. See if we can get our tech running here. I've got videos created for each of these 9 projects. I'm going to show you I'll run through 2 of them completely to see, so you can see what they are. And the others, we won't look at so much video, but we will get those posted eventually. Anyway, what we can do, skipping forward and back through this video, is see applying that concept of the inset channel to this landscape where we have really so much deposition obstructing the capacity of the bridge, and see if we get a graphic showing there that that's actually pretty much the height of the bar, and from one side all the way over, really reducing the capacity of the bridge and causing alignment issues with the channel eroding the far bank that was looking downstream. So what we do, it's not very exciting, but we dig not all the way down to the stream bed to regain that capacity, but just down to that floodplain stage. And that's a very fundamental concept in stream morphology, and if we can say nothing else besides this concept of a bankful channel and floodplain, then that's what it looks like in this kind of situation is to incorporate that compound channel form so that so the flows that are kind of the low and intermediate flows, they're not spread out across the whole base. They're confined to that narrower channel. And the narrow is not so important, but what the narrow gives you is deep. And depth of flow gives you sediment transport. So all these low and intermediate flows that are really about half of the sediment transport through this channel are going to be concentrated and deep, and the sediment transport is going to be improved by this compound channel form. So that's what it looks like at this project. And yeah, very, very simple. I think I spent the entire time out there, 3 days with the crew, but I don't think I did more than 15 minutes work. I just think, don't dig any deeper than this and just pull it back. It's very straightforward. Simple application of stream morphology to a bridge project. Moving over to Ottawa County. We just came in on the tail end of a bigger project here, or we're part of just the stabilization of it, but most of the project was redoing the piers on this that were badly corroded. And after all that work, the side slopes needed to be stabilized. And you know about stabilizing these side slopes where there's not much clearance, and is there any other way that we can come in with materials that might be available to do that and get in there where equipment access might not be so easy. So on this project, we used concrete cloth, which is a really cool material, which is flexible, comes in a roll, and you unroll it, put water on it, and it turns into a hard concrete. So it's about a half-inch thick, cuts like that, move it around fairly easily, hand labor, bit of equipment, and under the deck. Put fasteners just to keep it in place and keep each of the sections that are shingled together so it doesn't take a lot of strength. It has mass to it, so the water's not really going to be exerting a lot of force on it. And so far, we've had a number of high flows across it, and it seems to be stable. It was certainly easy to put in, so probably not a bad tool to have in the toolbox in special cases where you're dealing with limited clearance like that. Just saturating. It's concrete within kind of a honeycomb sandwich between two cloth layers. So after it dries, it's hard concrete. Walk on it and have water going. You wouldn't want to drive equipment over it, but it's concrete that's half-inch thick. And then, of course, it's just that sheet, so you have to key the upstream edges and make sure the water doesn't get underneath it. Would be a probable mode of failure. So that's what that one looks like, and kind of see what the videos are about there too. The other application we had for that material, we liked it so much, was inside of culverts, certainly in access issues here, and where we have corrosion or abrasion of the culvert, particularly corrugated metal pipe, and particularly where you've got kind of messy situations and water, and you might not want to go in and just put tar on the to stop the corrosion. Rolling this stuff out and fastening it to the metal pipe to line the culvert so that it stops the abrasion certainly, and reduces the oxygen back where there's corrosion, and fairly simple application that's been done on 2 projects in Ohio now that I know of, and another application of the concrete cloth. Now we're getting into some more fun stuff, which is really a very typical kind of an issue on northern Wayne County, where it's a stream that has migrated. Streams move. Streams are dynamic systems. We don't call stable streams things that are static. We call their stability a dynamic equilibrium. Meanders move. Outside bends erode, inside bends deposit. Generally, there's meander migration down valley over a long period of time. All natural and good, and that's how streams help how they maintain themselves in a good, healthy condition. It's a little bit of a problem, however, where we where we cross a road, which is not a dynamic system. So we've got that fixed point, and how do we manage that dynamic system at that fixed point? Well, the standard practice that's really used for directing flows in the stream restoration, that's risen to the top of all of the different kinds of practices that are tried, are these vein structures. And it's that shape constructed on one bank to direct the flow. And let's see if we have a video of that one. It'll be the kind of the longest project video that we have, but we'll see how those project videos are going to look on this one as well. So we define the problem at the site, where it's the lateral migration of the channel. The channel's moved from where it was originally, which is now causing alignment issues at the bridge. And scour around the abutment, where continuing maintenance issues are going in and trying to take that abrupt turn and put rock on it and maybe trying to straighten it out. But it's an ongoing problem from that misalignment now. So the first thing we do is realign the channel. And then the vein structure will be used to keep it in that position. Any material can be used for the vein structure. Logs are often used. Out west, they use big granite boulders and excavators with thumbs on them and stuff to try to stack up those bowling balls of rock. It's a mess to try to make these things out of rock. That's what I say now after working on these projects, whereas ODOT, there's a couple of people at ODOT that said, why don't we just use these big rock blocks, or concrete blocks? And yeah, that's absolutely outstanding material for building this structure. But if you're not trying to build something for kind of in a park for aesthetics or ecologically, and certainly from an engineering perspective, the block is just a superior material. This vein is constructed slightly upstream from the bridge, so we're creating a sill back into the bank. The other option there is to bring the vein all the way to the bridge itself. The geometry of these things is pretty well refined and modeled, and we've got that angle off of the bank that it just showed should be between 20 and 30 degrees. It has been found to be optimum. They're constructed at a slope with the highest point downstream at about the top of the bank on the downstream end, and then tapering down into the stream bed as it goes upstream at a really no more than a 7% slope. So 2 to 7% slope is what the slope is, and a 20 to 30 degree angle off the bank. That's the geometry we're looking for. And yeah, it's easy to do that with these blocks. Working in the water on this project is certainly one option. Water management winds up being a big deal. In different bed materials, it can be real problematic. So, and the constructability of these things almost comes down to what are you going to do managing the water of your work site. And we tried constructing first just in the water, but decided that no, we were going to. That was hard enough to work blind down in the muddy water, so wound up getting a pump to finish this project off. And I'm going to start skipping ahead here. And backfilling behind the block, so you stagger the next row up. Back behind the footer row is what we'll call that bottom row. And it just seems like we're cheating when we're using these blocks with a handle on the top and the guy just sitting comfortably in his excavator and setting them right where they are, spinning them around, comparing to trying to wrestle big limestone boulders or granite boulders into position. This is just, it's not pretty, but it sure does work. From an engineering perspective, it's a far superior material. Developed right here in Ohio. There we are, putting that layer all the way out there. So yeah, that footer layer has to go down below that maximum depth of scour One of the modes of failure would be that the water will come over the structure and undermine downstream from the block, and the block tumbles into the scour hole that develops. So the key aspect of the design is to get that footer down below the maximum depth of the scour and then stagger up, build up from that. See if we got, there we are, gave up on working in the water and got a pump out so we could see what we were doing. The other mode of failure would be on this kind of a design where it's tied into the bank is to have water coming up on the floodplain and going around the upstream end of the structure back down into the channel. That the way that they wind up being constructed is a gully will frequently cut around that if it's not stabilized the way we're stabilizing this one now, by really making sure that water is not going to cause a cut around the downstream end of the structure. So nice good erosion control there, and for kind of ecological, makes to turn it green. We like this practice of doing buried riprap, but to design the riprap as you need it, put it in place like what you would need to design it from an engineering perspective to be stable, and then cover it up with soil so it turns green. Seems to be one of the nicer ways for actually getting vegetation around streams. So there we go, what it looks like constructed. Skip ahead here and see if I can show you this one. And that's a picture I took just a few days ago on the bottom right there. But yeah, I think as far as what we have to say today, this is a really bread and butter kind of application. A single span bridge where the channel's migrated off to one side, and realign it and keep it aligned where we want it. Keep it aligned, keep the flow aligned with the bridge by putting a vein structure in, or some kind of a, we'll get into a couple of different variations of vein structures. So there's our standard practice. Moving over to Medina County, we've got a real high bed load stream flowing under a 3-span bridge that we constructed in 2 phases. The first phase was under the deck, and that was to get the channel aligned the way it needed to be. Again, working under the deck, we've got for clearance and those issues like we always have under bridge decks doing maintenance. So we tried this little remote control loader, which I think the guys had a lot of fun with. It works. And then the other phase of the project was a year later putting a cross vein in, and that's that structure that you see on the picture on the left. It's a vein with those same dimensions off the bank and at the same slope. There's just 2 of them that kind of meet in the middle. High bed load stream. Anything that we do with a high bed load stream, any mistakes that we make is going to be more problematic. We're going to get away with a lot less on a high bed load stream. And as we have gotten away with nothing here, that common mistake that we made on this bridge, which is made lots of places, it's really exaggerated on this one because of the high bed load, is by widening the channel out too much upstream. That streams are very insistent on that compound channel form, and especially when there's the high bed load. And the yellow arrows, the dimension there, I think that's where this channel was probably excavated out to that width in a trapezoidal form initially. And the channel didn't narrow itself up, didn't form a floodplain in that compound form right down the middle like we might have hoped. It's not. It builds a bar on one side and channel on the other, and then the bar continues to form and drive the channel migrating off into the bank, making a bad situation worse and worse, to where it wound up washing away the material on the side slopes, even around the piers, and poor alignment, and again, one bad thing leading to another, leading to another. all starting with that over-widening of the channel upstream rather than appreciating that compound bankful form. Yeah, so the first part was the first phase with the little loader, getting that, well, the three-span bridges, right in the bridge design manual, talks about using the middle span as for the channel, and the main flow, and then the dominant flow not around the piers and not, again, off in the side span. So most bridges are probably designed, if they can follow that guidance, to have that middle span corresponding with the bankful channel or the main channel, and the side channels only for higher flows. So we put rock back in where you can see it had eroded away to recreate what is already in the plans, what is already in the bridge design manual, is that cross-sectional shape underneath the bridge is a channel through the middle span and the side spans available only at a higher capacity. And that you can appreciate the importance of that for sediment transport on a stream like this, where you make something too wide, it's not only too wide, but that makes it shallow, and shallow flow doesn't move gravel, and it drops out and it forms bars. And we know all that, and we set out there to do that in our plans, and even we're saying to do all that, and we got to the second phase, and this is where the plans were saying to put the toe of that right bank, and look where we're digging. So, and we know this stuff, and we're not being, it's not anything new. I think it's an emphasis on what's important. It's very important. There's nothing more important from a stream dynamic point of view, is working with that concept of a bankful channel and higher stages for higher capacity. But it wasn't even on our radar when we were going out. Just the confusion, and we could make lots of excuses, and I don't want to do that because I'm probably more to blame than anybody, that I just wasn't drawing enough attention to upstream from this. Let's not repeat the same problem that caused all of this to begin with. And I didn't make a big enough deal of it, and the bank got excavated all the way back there and over-widened again. So same thing happened again. It promptly built a bar and is migrating off to the right again. So it's going to be a minor adjustment. We'll go back out there and we'll refill that bank out to where the dotted red line is, and it's not a big deal at this point, and it should work just fine. But I'd like to go back to that slide that John showed with all of those different resources talking about things to do with stream management around bridges, all the different stuff that we've learned from natural channel design and stream restoration. What are the key points? What are the fundamental concepts that we've got to get right for things to work? Well, this is one of them, and that's why I want to point this out. Is we had it right, but we weren't emphasizing this fundamental concept. We weren't giving it the emphasis that it needed. Moving along to another project in Wayne County, where this is another channel that migrated off to the side, so we've got to redirect it back into the alignment that we need. This one's at a two-span bridge. So it's a little bit different. My video going? So both spans here probably were initially designed to accommodate the design flow. Our bridge design procedures, drainage design, or bridge design manuals will talk about bridges having the design criteria. It will be a recurrence interval storm. So bridges have to be designed to pass some major amount of water, some rare storm event, which is fine. I don't want the roads to flood, but water is one of two things that bridges can be thought about having flow through them. Sediment being the other one. Bridges will be designed for water, and more often than not will fail or require maintenance because the sediment wasn't designed. Sediment transport wasn't thought through and designed well enough. So we've got a 2-span bridge here. I'm constructing the vein the same way as we've already seen the other vein constructed. And we didn't excavate out to the original capacity of that both spans, that we left that we left the second span as a floodplain span for that's available only for high flow, and we're going to keep the low and intermediate flows directed with the vein and the armoring that we had in there to go just through the one of the 2 spans. So the 1 span is similar to the bank full channel, so it works out well in this project. The 2 spans are far wider. If we want to construct a channel that is twice as wide as the natural channel out there is going to be working to maintain itself at that width, it's going to adjust. So that's the first element of this project is that it's a staged 2 culverts, staged culverts, or a floodplain culvert, where the one culvert is going to accommodate the low and intermediate flows, and the additional capacity will be over a floodplain and accessed only during high stages. So there we are, excavating only part of that floodplain, that bar off, leaving the rest of it as floodplain, and there it is after a period of time, after a year of high flows. With the alignment right. And this is looking upstream now. We didn't do any work downstream from this project. We just did the realigned it, kept the compound shape upstream. Downstream is actually where there was probably more of a fundamental problem going on, or that's where the problem was being realized, is because of the alignment problems upstream, the flow was turbulent enough through the culvert and downstream that there was a significant bar that formed down here. There was a bar really from here all the way across to the vegetation there, and the water was spread out across this entire channel. There we go. So here we are back upstream looking downstream, where the red dashed line and the arrow is pointing at the same spot in all 3 pictures. So before construction, after a few high flows, and after a year of high flows. That arrow pointing to a little tree that's there, so we know we've got the same reference point. In the top picture there, the high flows are going up over all of that deposited bar and spread out, and the sediment deposits. And that is really a limiting factor in the capacity of this bridge. So we're looking at the capacity of the bridge, and I know you're looking at that second culvert, and you're going to leave all that sediment in front of it, and it's going to reduce the capacity. It's not going to meet the design storm. The limiting factor on this one, I would submit, had resulted from the aggradation downstream that was resulting from the poor alignment upstream. And as a result of straightening the problem out upstream, that bar is gone away, and this channel is in a tough spot in the watershed where it's got a fair amount of gradient to it, and it's coming back down to the Kilbuck, kind of that lowlands, if you know that area at all, broad wetland valley. So it's losing gradient right here and looking for really any excuse to drop out materials if it's got an excuse. And so we took away that excuse. We straightened the water out, and the aggradation that it was giving us downstream is scoured, and we now have additional capacity through the really both spans. And a little closer look at the way it looks today. Moving up to a very different project, the far biggest watershed that we worked on in Fulton County, very northwest corner of Ohio. Back to that idea of the bankful channel. This is a 3-span bridge, but each of the spans is, or 2 of the spans is required to kind of be similar to that natural channel width. the bank full channel. We can't squeeze the entire low flow and intermediate flows through one of the 3 spans. So that means that we're going to have flow routinely going around the pier. It'd be nice to avoid, and it'd be nice to avoid because debris happens when we have flow going around piers. We're going to use a vein structure again, or actually a variation of the vein structure called a W-weir. And it's going to direct flow just like a vein does. It's going to be at that 20 to 30 degree angle just like a vein is at a 7% slope. And it's going to be configured so that it's set upstream from the pier, and the water is going to ride up on that kind of triangular shape and roll off the sides nice and gently without turbulence and be directed. We know how to direct water where we want it to go. If we want to have water directed not at a pier but through the clear span, we can do that, and this is how we do that. So this is a real standard practice that if you want water to divide and not carry the debris that it's carrying into the pier, put in one of these things. So it's under there. Maybe the top of it is be a foot submerged at this flow. And it's really just amazing. I think from the perspective, the best perspective is to be standing on the bridge over the pier and watch the water coming down towards you. And there's debris and things in the water. And on this one, one of the videos that I'm planning on posting for you is I had my camera all set up at that point above the pier and then ran upstream with a bag of oranges, which is the standard tool for fluvial geomorphic measurement and observation in the literature. Oranges, they sink down into the current and they follow the current. The wind doesn't blow them around. Bright colors so you can see them, but not plastic or anything that's going to be a problem anywhere. So I took my bag of oranges, threw it in directly above the pier is what I tried to do. So a shotgun of oranges coming down at me, and just gradually, no turbulence, no big deal. They just kind of split and go off between the spans. So that's one of the things that we get from this particular design and what it's refined is we don't want back eddies, we don't want turbulence, we want to be just that subtle shift of flow. So a really fun project for demonstrating that, because I know that on other projects that we've looked at, that the debris on piers is a common one. The most challenging project that we worked on by far was at 603 in Ashland County. And this is at a very difficult point in the watershed where it's a real steep watershed with lots of high banks recruiting a lot of coarse material, high energy stream, and it comes down to Broad River floodplain. More than that, it comes down to a Broad River floodplain that's been dammed. So it's got backwater from a reservoir. Reduced slope, reduced sediment transport, and that transition from the high energy right to the low energy is right where 603 crosses it. So there's nothing that the stream wants to do more under 603 than fill in with gravel. Of course, this is downstream looking upstream, and of course we tried to maximize the slope and the outlet for this as much as we could, but still fairly limited because there really wasn't a whole heck of a lot of slope. The fun part of the project is upstream that I'm going to show you. And so that's how to maximize the sediment transport at upstream from this thing. And we use the vein structure again, and the variation of it is a cross vein. And the way we build those things is dig down below the maximum depth of scour. And of course, I'm not going to ever use anything again except these blocks because they're so easy to put in there. And just from an engineering perspective, they are sound. And so I'm sorry you have to look at lots of videos of me very excited about hooking the handle on the block and moving them around so easily, because this is a big deal if you've ever been involved in a project where they've been trying to use boulders. So yeah, we're down below the maximum depth of scour and putting these footer blocks down. It's highest at the downstream end, so we actually are going to have 3 blocks stacked up there on top of these lowest ones. We looked at the one project where the vein stopped upstream from the bridgeways. Well, I think probably the better design is to bring the structure right to the abutments or right down to the bridge. And Yeah, fairly straightforward, stacking up the blocks. And what we're trying to do is accelerate the flow and have that maximum concentration and acceleration right at the entrance to the bridge. We can have it scour a hole rather than a bar right at the entrance to the bridge. That's what we built this thing in the hopes of achieving. So where it was and what we've got to do that. And I haven't got my videos put together for it yet, but we have had some high flows there. I can show you at least one picture of, and what it looks like after a number of flows. So 3 high flows out there, and you can see kind of the debris is up even higher than what the picture on the left is. And we're using awful lot of the stream's energy focused at that point to move sediment, rather than taking the channel that's upstream in the bankfold channel and then in a dynamic equilibrium, moving things around and widening out and slowing it down and taking its energy away. No, we're trying to put that energy right where we want to use it to move the sediment through. It's the first half of what I want to show you. The second half is kind of after these examples, what do we have to recommend? Lessons learned. Kind of lessons learned from the stream morphology, from the river engineering perspective, rather than the bridge perspective. It's where these two cross. What do we have to recommend? And from that stream morphology perspective, the way we think about streams is dimension, pattern, and profile. Cross-sectional dimension, meander pattern, crow's eye view, profile, the slope profile, longitudinal profile, and the materials. So let's go through and from that perspective organize some the recommendations. Starting with the last first, the materials. Yeah, there's some really fun materials out there, and any of the magazines that we get on the erosion control, they're worth exploring, and there's a lot of good things out there. We liked using the concrete cloth, especially in kind of special cases where there's limited access and those culvert linings, and I don't know what else you'd really use there. But I think that's what we can conclude about these erosion-resistant materials is probably limited to special cases. Other materials like the Flexamat, and you don't really need to recommend much about that. I don't think I see lots of projects out there using it. It's got its place, and fine. And then I think we kind of enter a whole nother arena. There's a whole nother toolbox of ways of making the material of banks more resistant to erosion, coming from the stream restoration perspective. If you want to make a erosion-resistant bank that will be really good trout habitat, you've got a lot of tools to choose from, and that's fine. There will be places on highway projects where lunker structures and delta veins and willow posts and all kinds of things, and in this case, core or coconut rolls, good bioengineering kinds of things, especially where you're trying to restore a stream and recreate that dynamic equilibrium, and things will move around eventually, and after the trees have been planted, and just kind of recreate that natural dynamic. We don't have a natural dynamic around bridges. We've got a fixed point. And rock and concrete, I think, have, when it comes right down to it, have a lot to be said for them when it comes to engineering these fixed points. Let's see if I have, yeah, for most of the erosion control work, the vast majority of erosion control work, bank work around bridges, I think that rock is probably going to rise to the top of the most recommended. And if we want to put more of an ecological benefit on it, turn it green, have some shade around the channel, cover the rock with soil, and it turns green. Another kind of oddball case, well, maybe it's not oddball because we kept seeing it on different projects that we went to evaluate, was the bare soil underneath the deck we don't get vegetation on that stuff, and you get gullies in it and erosion. And so how should it be fixed? Our recommendation is, well, does it need to be fixed? What we found more often than not was that the side slope had been stabilized with rock. And maybe it was a bit wide, or the channel shifted to one side or the other, and deposits of silt were over the top of the rock. And those deposits are under the deck. They've got shade, they're shade, they're not going to turn green. And so bare deposits of silt and high flows, you're going to get erosion in that silt. But what actually is the problem there? I don't think there's any problem for the bridge. The solution that I would recommend not doing is trying to stabilize the top of over the silt. So you've got a silt sandwich with the original riprap underneath, and then silt deposits, and then some kind of stabilization to stabilize the deposits. Maybe you want to do that, but I think I would recommend that you think hard about what the actual problem is that you're trying to solve by doing that. Dimension, okay. Number 4 here is, if we could say nothing else today, is that bank full channel is it's frequently not considered when constructing the channel dimension, the cross-sectional dimension in the vicinity of the bridge, upstream and downstream. And over-widening a section of channel reliably results in a bar forming and a smaller bank fold channel forming to one side, causing the poor alignment. So that is just such a common issue that if we could draw attention to, again, what do we emphasize is important so that it doesn't get overlooked and when things are actually moved around. This is a project up in Wood County where on the right picture, the entire area was over-widened and same process, bar form, channel to one side. If instead we could respect that bank full channel or utilize the hydraulics of that bank full channel to have sediment transport and stability, then it might look something more like that image on the left, where we're designing the channel so that low and intermediate flows are narrow, so that they're deep, and we get the capacity that we need at a higher stage. For 3-span bridges, what does that look like? Well, it's already in the specs, but it's overlooked too often, or not uncommonly, where the side spans, if they can be accessed during high flow, and the low and intermediate flow is directed through the mid-span. For culverts, practice that is not uncommon now is staged culverts. The top left corner photo there, where you've got one culvert that is similar in dimension to the natural channel, and then the multiple culverts, you'd have another one higher. We kind of did that on that one 2-stage culvert in Wayne County, where that right culvert, we left the floodplain bar in front of it. In Geauga County, we're hoping to retrofit some twin box culverts by putting a sill out in front of one of them. So again, at high flows, the flow is going to go through both culverts. The inlet will have the same capacity at the high stages, but low stages will have to flow over that sill, or won't flow over the sill, but go through just the one half there. So we're going to attempt a number of different materials to build that sill. And I was thinking that was a pretty nice idea. Proud of myself for coming up with that and recommending it, until just the other day when I looked at going through Google images of things, and someone up in Minnesota built one with this is a staged culvert. The third one over is lower. You look across the top of the culvert, you can see the one's lower. So we've got the stage culverts one, but then the higher stages, they put sills out in front of them too. So I'm not going to be able to lay claim to that design element to force this kind of multi-stage culverts. Okay, dimension, pattern, and profile. Pattern. Did I mention not to widen out the channel upstream from the bridge? It's going to mess us up in all different kinds of ways, including pattern. But what it leads to, just routinely, if we could say nothing else, I'm going to go back to that recommendation of don't do that, because of the things that it's going to mess up, it's going to be the pattern and alignment issues. And directing flow, we've got some really good experience and really good tools, and kind of the bread and butter tool in its different forms is a vane. So a vane or a cross vane or a W weir, we can direct flow around. Works really nice in, I'd say, particularly at bridges. The vanes, they're structures, so they're fixed in space. They're also fairly short, where compared to the effect that they have. So along a bridge, in a road right-of-way, where we can be working at the bridge, but pattern, that's a pretty long section of channel that is actually involved in the issue here. Vanes will, as the water rides up on the vane, it reduces the slope on that bank. And upstream, the length of the structure further upstream, maybe even two, you'll have reduced slope, reduced velocities, reduced shear, reduced erosion, will be affecting that pattern well upstream from where we're actually having to do the work. So maybe being able to limit the work to the right-of-way, but be addressing an issue that is on a longer stream reach than the vane construction itself. Yeah, and for piers, so common of a problem, and there's so many different ways that of this concept of that double vane structure called the W weir, putting that triangle pointed at the pier, dividing the flow. There's lots of different settings out there on big rivers and little rivers and different kinds of materials, but applying that concept of that 7% slope and those 20 to 30 degree angles pointing at a pier, there's going to be a lot of creative application, potential application out there for keeping debris away from our piers. Profile, be the last dimension that we're going to look at, and yeah, we want to not have the bed of grade, but move sediment transport through, maintain capacity of bridges, of course. So how do we use the flow with a cross vane to maximize sediment transport and maintain that depth of profile under the bridge? Well, another problem associated with the profile of bridges is not the aggradation of material, but the degradation of material. And I think that was one of the pictures even that John showed from the Ohio Bridge Maintenance Manual, was the bridge that had scoured down so low and was exposing footers. The vane structures can be used downstream from a bridge as a grade control structure. The diagram on the right is flowing north, so up in that picture. And so there's two vanes constructed downstream from the bridge to control the grade of the stream under the deck, around the piers. So that's what I think stream morphology can do for engineering around bridges. The last recommendation is just the reverse of that. My perspective is working with streams and working in entire watersheds and doing stream restoration. And I've always, for a long time, looked at bridges as an opportunity to do stream restoration on a watershed scale. that we've got incrementally throughout an entire watershed a number of bridges, a number of fixed points, a number of structures already on the channel. And I'm sure the biggest issue for stream restoration, the problem with our drainage networks, the reason our streams don't work well, the ecology of them is degraded, is because streams degrade. We have stormwater coming off of parking lots and doing higher peaks, and what that does is scour the bed down and lower the stream. And it's not at a point, it's the entire drainage network becomes lower. And is there a rational way for not doing stream restoration the way the vast majority of it's done now, is a few hundred feet here and a few hundred feet there, but is there a way that we can actually think about stream restoration that would be on a watershed scale? And I think one of the most promising opportunities is to incorporate the structures like we see here as grade control to prevent the incision of the channels throughout a drainage network incrementally throughout the entire drainage network and taking advantage of the road crossings. I had an awful lot of fun making these things. It's fun playing out in the stream and playing with the water, using its energy to do stuff. I hope you do too.
All right, we are, I guess, open for questions. Is that it? Are you guys ready? Okay, we have one question that's come in over the chat box. Okay, one question, one comment. So the question came in, it was, how do you prevent undermining the concrete cloth, particularly at the leading edge?
By keying it in, I think our design for that was to excavate down 1.5 foot trench around the perimeter of it, even on the downstream edge. But yeah, especially on the upstream edge, and laying the cloth down into that trench and then backfilling the trench with rock. On the design, on both the culvert design and the Ottawa site that was under the deck, there was concrete, at least, well, on the culverts, on the head wall, there was concrete on the upstream end. And there was a little rain gutter concrete apron on the Ottawa site for part of its length anyway. So we had that nice solid piece of concrete that we put the cloth over the top of and secured it, fastened it with the screws into the kind of the upstream facing surface of the head wall and that concrete apron. So yeah, that's certainly the mode of failure that I anticipate being the most likely, and needs to be addressed. However it can be addressed. That's how we did it.
Okay, and then there was just one comment later on. It's important to note that the use of the W weirs and crossings should be done by experienced designers. Getting these devices wrong can add greater instability. That's what we had online. So do we have any questions in the room?
With that particular picture there, I know that one had a lot of sediment buildup. Are you expecting that to kind of still be a drop-off or fill up with sediment?
Let me see if I can.
Like there was like a real gradual transfer.
Yeah. I mean, this is where it was after the first storm, and it's also where it is now after the third storm. That's the way we designed it to be.
Okay.
So whether I think it's going to be like that or I'm hoping it's going to be like that.
Okay, so I'm going to create that flush in that right there.
Yeah, we don't have a lot of energy to be working with, so we're trying to take as much of it out and concentrate it right there. And so, yeah, we do that by manipulating both convergent flows, by bringing the flows together, and by, in the profile, by dropping the water surface profile right into the bridge. So during the highest flow, well, during the low flow right here, that means that we've got a waterfall, and we don't want a waterfall. We don't want the water to be going vertically down into the bed and creating a scour pool just right there. We want the water to be more like a chute going gradually, like it does so well at that big Fulton County site with the W weir, just gradual shifting of the water. So yeah, I think one of the adjustments that I would actually like to make on this project is to see if we can get rid of some of that turbulent flow. And
I just didn't know if you had to do that one particularly because there's so much sediment. Not really see that there's structure or not.
Accelerate and concentrate the flow is the phrase that I've been using as kind of the design objective for the structure.
Well, I will tell you, District 3, Ashland County, is very happy because in those 3 events, they would have normally had to close that road. They have not had to close the road.
So there was another online question, and I believe it applies to this same slide that's up. Have you seen any undercutting issues of the concrete block at the point of the V of the vein?
No. We anticipate that, I mean, we've got a drop right there, so it is a scour pool area. So to design against that, we put the footer block as low as we think it needs to be. In addition to that, we put on this one another block, and I wonder if you can kind of see it here. There's the handle of another block that is within the structure. So it, again, won't have so much drop right at that point, but more of a chute flow at an angle off towards down into the bridge rather than directly down into the bed. Another issue that we've gotten with the scour around the points there is we've got them designed real well for the maximum flows, thinking maximum scour and maximum erosion with the maximum energy of the highest flows, but that is not necessarily the case. As you can imagine in this photo here, where during a fairly low flow, we've got that drop that will disappear during higher flows. So during intermediate flows and even lower flows around the point of the vein structure, I think we have to engineer and armor there for those lower and intermediate flows. The place that we really had to armor for that is on the Fulton County project, which is in a sand bed channel, which is a really different type of stream to be building these things because the sand erodes so easily. We put notches in the V, so in between, at the upstream end of the block, instead of having the top row of blocks all tight together, we left a foot and a half gap between some of the blocks. And that's done in trout habitat kinds of structures for migration and all well and good. Maybe bed load transport through those might be advantages to it. But what it wound up being is just during low flows in that sand bed channel, because there was so much energy going through those narrow openings of just a foot of flow depth, that it was scouring not just downstream from where it was going through those openings, but also upstream. So we wound up armoring at the upstream end of the cross vein or the W weir, downstream from the structure, inside the structure, and also upstream from it and around the sides.
And we have one last one come in. What waterway permits were used? It says RGPB and were PCNs needed?
We got the guru in the back of the room if you want, John.
So what waterway permits were utilized? So that's where we utilized the folks at EMH&T to work with the folks in the Office of Environmental Services to obtain the proper permit. And well, a little bit knowledgeable and fairly ignorant. Would you mind speaking to?
I don't remember which one specifically we used for each project, but it was a mix. We used Nationwide 3 on one of them. We used RGPB on one of them. We used
27.
Nationwide 27 on one of them. I think we used the bank stabilization nationwide. And I think one of the recommendations that came out of this process is that we will be meeting with the Corps discuss how to incorporate these types of projects into our RGP because they're kind of unique. They're kind of like maintenance projects because they're trying to maintain the capacity of the bridge, but they also have a stream restoration component to them. So the Corps initially didn't know how to respond to them because they were a weird combination of project types. So our goal would be to modify our RGP to be more streamlined to permitting these types of activities. So A, we can get them on the ground faster, and then get the benefits of the stream and infrastructure faster. But whoever that is, we can send them the copies of the permits we obtained for each project if they want. But yeah, they were all permitted in water. Was there a question about PCN? I think we had a couple PCN pre-construction notifications to the Army Corps for these for the 4 permits. Which again, if we can modify our RGP, hopefully eliminate that in most circumstances on a more routine type, and only in more extreme circumstances, we actually have to go to the actual Army Corps for that. A mix.
So can you, because District 8 is having a hard time, they've got a whole bunch, they're having a hard time.
That question came from District 8. They
Okay.
said they were able to.
Okay.
I was just imagining there's a microphone somewhere, right?
It's a phone.
Yeah, it's a phone. Oh, what an interesting microphone. No.
So that last project that we were looking at, the slides, there's 900 feet of channel involved in that, and certainly justifiably more permitting. I think the more typical projects that not only we were involved in doing as projects, but problems that we went out and had people wanting to address would be addressed by something like this. A single vein just on the upstream side of the channel or upstream side of the bridge, and some in-channel work.
But you're also, I want you guys to both address this. We've done videos because we don't want this to sit on a shelf. We want to use it. That's why we're doing the streamlining with the permitting. Our maintenance crews did an excellent job. As a matter of fact, what you did not talk about is all of our county garages, when they go out and look at a job, have to look at force account limits to decide whether they should do the work. By our maintenance crews doing the work, there was approximately 75% savings over what had been estimated in the original force account amount.
So yeah, originally when we were sitting down trying, one of the limitations we have with the county crews is it's difficult for them to try and dedicate a crew of 3 or 4 or more people for 2 weeks at a time when they have all these other activities that they need to do. So a couple things. Let's try and get these to a scale where they can do them in less than that, if at all possible. So we started to, go through some of the initial engineering based on experience from stream restoration projects. Originally thinking that these might be 1.5 to 2 weeks sort of projects. Throwing estimates at them, maybe $35,000, $40,000 for something typical like this. Through some of the innovation, utilization of those materials, they're maybe a little more skilled than we were anticipating they would be. Those sort of things. This project here, what, 3 to 4 days?
Yeah, mobilization and all of that, 3 or 4 days. And again, you get the crews started on something and they take off. So what do I do while I'm out there besides shoot video? I timed them on the construction of this weir, or the single arm vane. And we started one morning, and 4 hours and 45 minutes later, this vane structure was complete. So that's not the riprap work we did. That's not the mobilization or anything like that, or seeding, but actual construction of the vane structure was less than 5 hours.
Total, looking at the work order summaries, total investment on something like this more in the $8,000 to $10,000 range versus the $35,000 to $40,000. And within that reasonable time frame, with materials that they feel like they can acquire, move, fairly low cost, and really able to get these things in. So we were quite pleased from that perspective.
Well, and you guys are doing videos.
Yes.
So that we can take them out to our maintenance crews, and they can duplicate what's been done. Correct? You want to speak to that? Nope?
I'll comment on that.
Okay.
I think you're going to have a challenge for folks understanding you're not dealing with geomorphologists. They're going to have a little bit of challenge understanding how to define the maximum depth of scour, because you're only looking at a creek when it's dry. Nobody's out standing in the river during flood stage to understand your bed load. Let's see what else we got. I think you'll have a little bit of a challenge. They need to be able to understand they have to walk up and downstream, sometimes a mile in each direction, to determine your state of your creek. If you have a head cut coming at the project, your maximum depth of scour will be significantly different. So I think you got a great start there. I think there needs to be an ability for the districts to call on someone to come out and meet and look at their site specific. And once they've been through a couple cases, I think your districts can do this. Because the difference between a grading and a degrading channel, the design is completely different. And they may not always know how to recognize that, because the channel could be depositing sediment at a bridge, but everywhere else it could be degrading. So I think it needs a little bit of care, because what I see in bridges in my previous job is a lot of times they were still struggling to get the riprap in correctly. When you have improper gradation, improper use of fabric, sometimes we still struggle with the fundamentals. And so you've got to be able to do the riprap correctly, and then you also have to try this. And I think this is a lot simpler than placing riprap, honestly. Placing riprap is a hard science.
Do you want to comment before I talk about some of the recommendations we made? So, well, look,
Go for it.
So, real quick, some of the recommendations we made in the report were, it's a challenge to build one of these things for the first time out in wet. So perhaps there could be some trainings where it might be done in the dry, not only with engineers but county staff, to talk about constructing these sorts of issues, these sorts of practices. So I think continuing that, documenting what we've done, but then providing education trainings, might be a part of that as well. Did you want to speak to any other?
Well, I think that certainly appreciate that streams are complicated systems and never do enough engineering, and it would be nice to have a fluvial geomorphologist on every project at all times. On the other hand, we went into these projects anticipating a certain level of effort was going to be required to get these things built. We were always anticipating that the maintenance crews would do the work, and so what did we have to do to support them? And I know I was surprised, very surprised at the competencies of these guys, that given the right information, and we've thought about what that information needs to be, but yeah, there definitely has to be some information to get them headed in the right direction. But these guys are good. They're good operators out there. They know earthwork.
I have a question. How were these things designed initially? Were they just rules of thumb and you go out and place them just by looking empirically, or were they designed with a model, like a head model or a 2D model, or I guess I struggle with how these things are.
And no hydraulic modeling was done, well, with the exception of maybe that last project where the sediment transport was so much. But on a project like we're looking at now, no modeling was done, and we did not even go back to find out what the initial flow capacity of the bridge was. The approach that we took to it is that by the work we were going to do out there, we were going to improve the capacity over what it was and reduce the maintenance required to keep that improved capacity. The design standards that we have, and we do have them for these structures, are pretty much what I've said all day now, where there's 30%, 20 to 30% slope and 7%, or 20 to 30 angle and 7% slope, and yeah, apply those dimensions to the top of the bank, and that's, I'd say, pretty much an empirical design.
I think earlier on, before maybe Dan joined, there was some modeling done to look at the existing condition, capacity, and then for some reason HY8 is the name of it was a very simple hydraulic approach to make sure that we were at a minimum improving the capacity, that by putting in the structure we weren't going to reduce capacity. And I think maybe that was part of the floodplain permitting process that might have been required for some of these. EMH&T was involved in that aspect of it, so I have to clarify with them. But it's actually written, it's in the appendices of the report, so I can go back and check that out. But it wasn't a TEC-RAS model by any means.
Sure, I guess I struggle with, we should probably fully understand before we go implementing these everywhere, what's going on in design this chart as well. These structures are going to have an impact. The way that you're, well, even at the high flow, whether it's a 1D or a 2D model, especially when we approach FEMA aids and your model is going to struggle to understand that, no matter what you're running. I totally agree with that. $100,000 in the model, and it's not going to be able to digest that. It's going to have to be a little bit of both.
Okay. You mean monitoring as well as modeling?
Modeling. The models don't do very well with these type of structures.
When you
This is definitely probably too small.
Well, and that's where I would say, that's why we have another project that has come off of this, the streamlining project, where we are looking, because we know this is a good beginning point, but we know there's more work to be done. We're not saying maintenance forces are going to go out there and do this now, but we're continuing the work. We're continuing to do the videos. We're continuing, you developed a spreadsheet as well, Excel, and we'll have to do training. And that's part of the streamlining. That's part of the new permitting process. We're looking holistically at this and some of the other changes, how we actually design bridges, build them. So, and that's, I won't go into all of that, but we are continuing studying this, because we do know when we can look at our director and say, this will save us about 75% in the budget, and he's always talking about force account limits, and we can take it down, this is worth the research investment to continue looking at it. So, Dan, if you wouldn't mind going to the very end. I don't want to cut anybody off. Do we have more questions? Michelle, do we have questions?
Yes, you got a two-part question coming in. Are you using any rock and infill between your vein arm and the stream bank, or just compacted soil?
No, I went at the very end.
I went to the very beginning.
Yeah.
The other end.
Will you read that again?
So, it was, are you using any rock as infill between your vein arm and the stream bank, or just compacted soil?
No is the answer to the question, unless we would talk about using the material like the gravel that might be excavated from the stream bed. So it's whatever material we have on hand is put back there. And again, with the exception of just downstream from the structure, if we're tying the vein into the bank with that arm going back into the bank, we don't want water going over the floodplain and falling down into the channel just downstream from the vein. So that bank right there, definitely rock. And we had the one example where we did go to a good effort of getting the riprap design between the bridge and the vein, so downstream from the vein. Kind of upstream from that point, no. And I don't believe that there's even a need to put any fill in there. We put fill in there because because we've got more than enough material on hand, and just to get things to balance, it's kind of almost spoiling it in there. A fine place for it, but I don't think it's necessary for the hydraulic functioning of the structure. And the way the flows work, the high flows are pretty quiet on that bank. And if anything, I would, if we didn't put any material there, I suspect that we'd have deposition in a bank building there and depositing.
Second part of that was, have you seen any issues with the stability of your vein arms, or have they been fairly stable and remain vertical?
Yeah, the surprise for me, I guess, would be scour upstream from the structure. So like where you might have during those low, just a little bit above low flow, shear stresses where you have such steep slopes around those concentrated patterns at the point of the structure. You can get a scour hole, especially in that sand bed material, but in coarser material too, you can get some scour upstream from the structure. So the standards and specs that have been developed and people read about, a lot of that stuff is developed out west in the Rocky Mountain states, and where there's so much coarse material coming down the streams, much more than we have to contend with. So what their only concern is, and the only concern expressed in a lot of this stuff that's written about these, is to make sure that toe, the downstream toe of the structure, is well stabilized, and the scour hole won't develop there, and having the block tip over forward into that scour hole. Where we also have to be cognizant of the scour that can develop in our lower bed load streams upstream from these structures, not necessarily during high flow, but during these other events where we might get the scour hole around there. And that again is the other good question was asking about, do we ever have scour at the upstream point of the cross veins and the W weirs? And yeah, that would be the place in particular where I would want to get some rock up around the upstream side of the block so that the scour holes weren't developing there, which is not difficult to do, just anticipating it. And good idea.
Any more questions? All right, I want to thank you all for attending. I want to let you know this presentation will be found on our website. The report will be out there in 2 to 3 weeks if you want to go and look at the report. We are continuing. We do believe as an agency that this is going to be very cost beneficial for us to do. So we have another research project with OSU that came off of this, and it's the streamlining. So we're actually using our county crews to go out, look at stuff with Dan. We're making videos. Training will be a big part of it, but that should be done maybe, we hope, in a year or two. This has already been a almost 4-year project. We didn't think it would be that long when we started out, but we learned a lot of lessons along the way, and that's what research is about. So if you're interested in learning more, please go out to our website. Thank you.
Great work.